Welcome back. Today's topic is computation of magnetic fields for different current configurations. In the last video lecture, we have seen about magnetic forces and also what Biot-Savart's law states. We have seen that Biot-Savart's law gives us the expression for computing magnetic flux density due to a current element. In this video lecture, we will see how to compute magnetic flux density for different current configurations. I hope that you will be able to apply Biot-Savart's law for computing the same. Having said this, a quick recap of Biot-Savart's law. It says that the magnetic flux density due to a current element is given by this particular expression. Right, we have seen this one in the last class, and if we want over the entire length, what we will do, we will integrate it over the entire length, mu I by 4 pi r square into dl into ur, isn't it? And if we want only the magnitude, what we will do, we will integrate it over the entire length, mu I, this is 4 pi r square into dl into sine alpha, where alpha is the angle between the current element and the point of concentration, isn't it? And if you want h, we will do very simple b by mu. So this is what we have seen in the last lecture. So I will skip these slides and I'll directly move on to problems. We will see the first problem. See, find an expression for magnetic field intensity at the center of a circular wire carrying a current I in the anti-clockwise direction. The direction of circle, I think this is the radius of the circle. The radius of the circle is A and the wire is in XY plane. Okay. So with this information which we do have, let's try to calculate the magnetic field intensity. So what I will do now is, see, I have corrected this one. So the radius of the circle is now A and the wire is in XY plane. So now what I am supposed to do, I'll take an XYZ plane. They say that there is a circular wire which is in XY plane and it is carrying a current of I in the clockwise direction. So I'll take this XY plane. So this is a plane I'll take. So it seems that there is a circular wire which is in XY plane. Okay, this is the circular wire which is carrying current in this fashion I, and it is in XY plane only. Okay, so what they want is expression for magnetic field intensity at the center of the circular wire. So this is the center of circular wire. So normally the magnetic field, as you all know, since this is a current, the magnetic field will be projected towards in this fashion, right? So we need to determine what is the magnetic field intensity which is there due to this circular current. Okay, so this is the figure now. See, this is your XY plane and this is the circular wire. Okay, and the radius of the wire is A and the current is flowing in anti-clockwise direction. And see, if I consider a point P and then I'll integrate it over the entire thing. Okay, so this is, I'll consider a small differential element dl and then I'll integrate it over entire circumference of the circle. So what I am going to do, I'll consider a dl and next I'll integrate it over entire length. Here what is the entire length of the wire? It is nothing but circumference of the wire. Circumference of circle. Okay. So now, so if you see, since it is given that the wire is in XY plane, the current element is considered to be in XY plane. So the field will be along the axis which is perpendicular to that of XY plane. So we have seen that in the previous figure that the field intensity vector will be across Z plane, because xy plane, perpendicular to xy plane is z prime. So we will get magnetic field intensity across the z plane. So also it is given that the radius of the circular wire is a meters. So the center of circular wire from any point on the wire will be at a distance of a meters, right? So it is just like as already I mentioned. This is my point of consideration. So this is my current element. So whatever may be the current element, if we consider this one, if you consider this one, or if you consider this one, all are at a distance of a. And I need to determine what is the h vector here. We know that h vector is given by this particular formula. dh is equal to I by 4 pi r square dl, which is a differential length, into ur bar, isn't it? See, we have already seen that this is results in a vector which is perpendicular to both of these things, right? So what I am doing is dl is a combination of dl, right? So this vector, what I am writing it as, the resultant vector will be in the direction of z direction. Okay, so that's why I'll consider the magnitude of this one is dl and this magnitude is 1, and the direction of the resultant direction will be in the z direction. By observation only I have written this one. Okay, now I will integrate this one over the entire length of L, which is nothing but circumference of my wire. See, this is my expression, right? What was my expression? dh is equal to idl by 4 pi r square into uz, because the field is across the z axis. Now what I am going to do, I am removing, it will become integral over the entire length. If you see the entire length, it is across the circumference, right? So first of all, let me remove these things. IA is also independent of length here, right? Because all the points, they are at equidistant A. So this is my expression now. So over the entire length, what is my entire length? It is circumference of circle, right? This is nothing but entire length of conductor. See, my conductor was in this fashion, circular fashion. So I have a dl is this one. If I want the entire length, what I should do? I should consider the entire length in circumference. So what is the circumference of this circle? The radius is a, so circumference is 2 pi a, right? So if I substitute this one, this is my field intensity. 4 pi, 2 pi will go, you will get 2, you will get here a. So this is my expression for magnetic field intensity through a current I in the circular wire. Okay. Now, coming to the second problem. You see the second problem? Find the flux density and field intensity at any point, at a point P due to a straight conductor carrying a current I as shown in the figure below. It is above. Okay. So now this is a conductor. Okay. What I have written is a conductor. Now I am considering a point P, which is at a distance of, shortest distance is h, and the two ends of the conductor are making an angle of alpha 1 and alpha 2. Okay, and I'll assume that the current is flowing in this fashion. Okay, and this point is, this is R. Okay, now we need to determine the flux density or field intensity, both B and H, at this point P, where this is the current element I into dl, and dl it is varying over this entire length. Okay, now how to solve this particular problem? Now this is a simple representation of this particular problem. If you carefully see, I'll assume that the conductor is in X plane. It is my own assumption, so I'll consider that the conductor is in X plane, and let P be any point at a distance of h from the straight conductor in xy plane. I'll consider z is equal to 0. So what I'll do is nothing but I'll take x plane and I'll consider y plane and I'll consider z plane. I'll see that this is my conductor in x direction. Okay, and I'll consider a point here which is in xy plane itself. I'm not considering any z plane. Okay, so this particular point is making a distance of, shortest distance is h, and this entire length, if you consider, it is entire length is L. So this is L1, this is L minus L1. Okay, so this is A, this is B, I'll take it as O. Okay, so now this two ends are making two different angles. One is alpha 1, the other one is alpha 2. Okay, I'll assume that the angles made by these two are alpha 1 and alpha 2. Okay, now if you carefully see, I'll consider a small length here. I'll consider a small length here, and then I will integrate it over this entire length. Okay, so it's easier for me rather than to integrate over length. Rather than integrating over the length, I'll consider this angle and I will integrate it from alpha 1 to alpha 2. That will be the easier fashion for me. So I'll try this one now. So first of all, let's see the differential length vector. I'll consider it as dl, and it is lying across x-axis. So I'll consider a small length dx across ux. I'll draw the figure again. This is my point P, and this is my entire length. I'm assuming that it is A, this is B, and this is O. This is L1, and this is L1, L minus L1. So I'll consider only a small length dx. This is my small length dx, which is at a distance of x from one point. Okay, and this point, it is L1 minus x. Okay, so I'll consider this particular element. I'll consider that this angle made is theta. So I'll consider this one now. So this differential element dl, its length is dx and it is along x axis. So I'll take it as dx into ux, and the current through this one I'll take it as I. Okay. So now the unit vector which is joining this current element to this particular point P, I'll assume that the distance is r from here to here, and the unit vector is ur. Okay. Now determining the magnetic field intensity. You know the formula, right? This is a simple formula. What is dl now? dl is nothing but dx into ux bar, right? So I'll take it as dx into ux bar. So if you can see from this figure, ux into ur bar, which is nothing but ux was in this fashion, ur was in this fashion. Now the cross product of these two is nothing but the angle sine theta into the resultant vector will be along the axis, which is not in x and y, perpendicular to both x and y. So it will be uz direction, because it was in x, because it was in y, so it will be in uz direction. So that's why this is my expression. Okay. Now in this one, if you carefully see, I is independent of length, 4 pi is independent of length, but r, if you see this entire point, if I am considering dx here, right, this is my r. If I consider here, this is my r. If I consider here, this is my r. So r is varying. Alpha also will be varying. So if I consider entire length, what will be the varying terms? Dx will be varying, r will be varying, sine theta will be varying. So that's fine. I have removed the unnecessary terms and I am applying integral only to these terms or the entire length. Okay. Before going any further, let's see this small triangle now. AB. This is my O point, this is my B point, this is my small length, right, dx, this is my r, this was my theta, entire length was L, this length was L1, this length was x, so this length was L1 minus x, this was r. So in this triangle, I'll take it as D, and triangle DOP, if you see, what is cos theta? Cos theta is L1 minus x by r, right? And this is h, right? And what is tan theta? It is h by L1 minus x. So I'll utilize these formula. And what is sine theta? It is h by r. I'll utilize these things. So first of all, I'll calculate h. See, What is R? R is nothing but h by sine theta, right? Which is nothing but h cosecant theta. This is one thing. The other one is L1 minus x. L1 minus x is equal to h cot theta, right? So if you differentiate this, what will you get? Dx is equal to h into cot theta. It is cosecant square theta d theta, right? Actually, yeah. I substitute these two terms, dx and r, in this equation. So this was my equation, earlier equation. What was my equation? Yeah. H is equal to I by 4 pi over the entire length. It was dx sine theta dx by r square into u z bar. So sine theta, I do have sine theta. Dx, I do have h cosecant square theta d theta. This is h cosecant square cosecant theta whole square. I have substituted these two terms. So over the entire length, if you can carefully see, this theta 1, this theta should be varied from, this is theta 1 and this is theta 2, right? So theta 1 to theta 2. If you simplify, you will get only sine h, sine theta. H will be remaining, h I have sent it outside. So this is my expression. What is the integral of sine theta? Cos theta. So you will get cos theta 1 minus cos theta 2. So this is theta 1 and theta 2. But actually, if I take it as alpha 1 and if I take it as alpha 2, alpha 1 is equal to theta 1, whereas alpha 2 is equal to pi minus theta 2. If I substitute these terms, what the expression which I will be getting? I will be getting, this is my final expression. And if you want b, you are supposed to multiply it with a. Okay. I hope now you have understood about these things. And I hope that you are able to compute magnetic flux density for different current configurations. That's it for today. In the next class, we will see some more problems on this magnetic flux density. Thank you.